Welcome back, Focus Learners. Today, we're diving deep into the absolute core of database architecture to explore the ultimate safety net for your data, serialization. If you've ever built a back-end system and wondered how databases manage to keep data perfectly consistent, even when thousands of users are reading and writing at the exact same millisecond, well, you're in the right place. In this explainer, we're going to unpack the strongest transaction isolation model available to engineers today. Let's get into it.
All right, here's our roadmap for the system design journey today. 1. The concurrency problem. 2. What is serializability? 3. Actual serial execution. 4. Two-phase locking. 5. Serializable snapshot isolation. And finally, 6. The cost of correctness.
Let's kick things off with Section 1, the concurrency problem. Okay, to really appreciate a robust solution, we first kind of need to see a system break under pressure, right? So picture this. You've just written some back-end code, you've tested it, and in isolation, it looks absolutely perfect. It checks a condition, and if that condition is met, it updates a database record. But what happens when reality hits, and two users trigger that exact same, perfectly valid code at the exact same time? Let's look at a classic scenario from a hospital on-call scheduling system. Alice and Bob are both doctors, and they're both currently on call, but they're both feeling sick. So they independently decide to request leave. And, as luck would have it, they happen to click the Go Off Call button at roughly the exact same time. So our application starts a transaction. It first runs a select query to see how many doctors are currently on call. Both Alice's transaction and Bob's transaction check the database concurrently, and they both get the same answer. 2. The application logic says, hey, as long as there are at least 2 doctors on call, it's totally safe for one to leave. So Alice's transaction safely updates her record to take herself off call. Bob's transaction acts on that exact same premise and updates his record to take himself off call. They both commit successfully, and the result, the hospital now literally has 0 coverage. No one is on call. The application logic was sound, but the concurrent execution completely broke the business rule.
Now, what we just witnessed there, that wasn't a dirty write. And actually, it's not a standard lost update either, because Alice and Bob modified completely different database records. This is a much more subtle anomaly. We call it write skew. Write skew happens when a transaction reads some data, makes a decision based on that data, and then executes a write. But by the time that write is finally committed, the original premise, in our case, that 2 doctors were on call, well, it's no longer true. And the scary part? This kind of bug slips right past weaker database isolation levels, like read committed or even snapshot isolation.
Which brings us to Section 2. What is serializability? So, to prevent subtle bugs like write skew and phantoms, database engineers reach for the gold standard of correctness. And the crucial mental model shift here is this. Serializability guarantees absolute isolation. It basically means the database guarantees that even though transactions might actually be executing in parallel under the hood, the final result is mathematically identical to a world where they ran serially, meaning completely one at a time without any concurrency whatsoever. It's really the best of both worlds. Concurring execution allows for this messy, overlapping interleaving of reads and writes, which, is amazing for performance, but opens the door to race conditions. Serial execution, on the other hand, is clean and totally safe, but slow. Serializability gives you the safety of one-at-a-time execution, while the database still runs things simultaneously. It lets you, the developer, safely pretend you are the only person using the database. You just write your code, and the database itself handles all the complex conflict prevention. Let's look at how this works in Section 3, actual serial execution. So how did databases actually achieve this guarantee under the hood? Well, the first, most brute force way is to literally just execute transactions serially, basically on a single thread, one at a time. No locks, no complex concurrency management, just one single processing queue. Now, I know that sounds crazy for a high-performance system, but it actually became feasible recently because RAM got incredibly cheap. If your entire active data set fits in memory, you don't have to wait for slow disk reads. But catch this, there are strict constraints. Your transactions must be extremely short because a single slow transaction will stall the entire database. Your throughput is strictly bottlenecked to a single CPU core. And finally, to avoid waiting for network round trips between the application and the database during a transaction, the logic usually has to be bundled up into stored procedures that run entirely inside the database engine. Moving on to Section 4, two-phase locking. Since running everything on a single thread has some pretty severe hardware limitations, let's explore the traditional approach. This one dominated databases for over 30 years. It's called two-phase locking, or 2PL. Unlike the single-threaded approach, 2PL is highly pessimistic. The idea here is that if a transaction wants to access data, it must first lock it to stop anyone else from messing with it. It happens in two phases. In phase 1, as the transaction executes, it steadily acquires locks. If it's just reading, it gets a shared lock. If it's writing, it demands an exclusive lock. Then, in phase 2, which only happens at the very end when the transaction commits or aborts, all of those locks are finally released. It's very much an all-or-nothing approach to keeping data safe.
And this brilliantly illustrates the massive difference between two-phase locking and weaker isolation levels. In weaker levels, a read doesn't stop someone else from writing. But in 2PL, writers block readers and readers block writers. Full stop. If I'm reading a row, you absolutely cannot update it until I am completely finished. Because of this extreme locking, 2PL often leads to pretty terrible performance overhead. Transactions just spend a lot of time waiting in line for locks. Plus, deadlocks are incredibly common here. Like, transaction A is waiting for a lock held by B, and B is waiting for a lock held by A. The database has to constantly look for these deadlocks and force one of them to abort and retry.
Section 5. Serializable snapshot isolation.
Okay, so 2PL can be painfully slow, and serial execution is super restrictive. Because of that, researchers developed a modern approach that tries to give us the absolute safety of serializability, but with the blazing speed of weak isolation. It's called serializable snapshot isolation, or SSI. This is an optimistic concurrency control technique. Instead of pessimistically locking rows and blocking everyone else, SSI lets transactions run wild and free based on a consistent snapshot of the database. It optimistically assumes, hey, everything's going to be fine. But behind the scenes, it lays down these non-blocking tripwires. When a transaction finally attempts to commit, the database checks those tripwires to see if any conflicts actually happened. If another transaction swooped in and changed the data you were relying on, the conflict is detected, your transaction gets aborted, and it has to be retried. Only mathematically safe transactions are allowed to pass.
Now, what's really interesting here is how the database tracks this. Let's say a transaction, we'll call it transaction 43, reads the database and sees that Alice is still on call. But concurrently, transaction 42 has just updated Alice's record to take her off call. Transaction 43 doesn't know this yet because it's happily looking at an older snapshot of the data. But the database is keeping track. When transaction 43 finally tries to commit, the database checks the logs and sees, wait a minute, the data transaction 43 relied on was just modified and committed by transaction 42. Because the premise is now stale, the database triggers an abort for transaction 43. Boom, write skew is prevented.
The database also has to handle the exact reverse scenario. What if another transaction modifies data immediately after you read it? To do this efficiently, SSU uses something called index range locks. But listen, unlike the heavy, paralyzing locks we saw in two-phase locking, these don't block anything. They basically just act as sticky notes or notifications attached to a search index. So, if transaction 42 is reading the status of doctors on shift 1234, it leaves a little non-blocking note on the index for shift 1234. Later, when transaction 43 comes along and writes a change to that exact shift, it hits that tripwire. The database immediately notifies the transaction manager that transaction 42's earlier read is now invalid. Whoever tries to commit last, they get rejected.
Which brings us to our final section, Section 6, the cost of correctness.
You know, there are no silver bullets in system design, so let's quickly recap the main trade-offs of these three approaches. Every engineer needs to understand that absolute safety isn't free. First up, actual serial execution. It's beautifully simple and single-threaded, but it heavily restricts you to single-core throughput and forces you to fit your active data set entirely in RAM. Second, two-phase locking. This is your battle-tested pessimistic approach. It absolutely keeps your data safe, but you pay a massive cost in query latency, blocking, and dealing with deadlocks. And third, serializable snapshot isolation, the modern optimistic alternative. It avoids blocking entirely, but if your system has a high rate of read-write conflicts, your application is going to spend a ton of CPU cycles constantly aborting and retrying transactions.
So, this brings us to the ultimate question for your own architecture. Serializability guarantees that you will never, ever see a write skew, a phantom read, or a lost update. It literally allows developers to sleep peacefully at night. But is your system willing to pay the price? You have to weigh the costs. Whether that's the hardware limitations of a single thread, the painful waiting and deadlocks of pessimistic locks, or the wasted network overhead of retrying optimistic transactions. For financial ledgers and medical scheduling systems, the cost is absolutely worth it. For social media likes, probably not.
Consider your data, consider your trade-offs, and design wisely. That's it for this explainer. Keep learning, keep building, and we will see you next time.